Welcome back to class 21. Here's an example 6.4. We're going to consider, well, we don't need to know what happened in example 3.13, but in which oxygen is heated from 300 degrees to 1500 degrees Kelvin. Assume that during this process, the pressure dropped from 200 to 150 kilopascals. Calculate the change in entropy. All right, so we're going to do this in 3 separate ways. You don't always have to do it 3 separate ways, but you can, so we might as well figure out how that is. 2 of them are kind of annoying. I'm trying to think which one I would consider the most accurate. I am going to go ahead and do the thing that we just referred to in the previous video, where we introduced some additional things about the entropy change in an ideal gas, right? So in section 6.6, we introduced this information. So let's take a look. This is actually the third method that I describe in that video to find the entropy. All right, and so that's going to be, so I'm looking, okay, using table A8. Right. So we're going to look up for these 2 temperatures. So at T is equal to, I'll call it T1, is equal to 300 degrees Kelvin. We're going to look up the ST. We'll call it ST10, right? And then we'll also look up for T2 at 1500 degrees Kelvin. We'll look up what that, trying to remember what I just called it a second ago. The standard entropy, right? So let's look at standard entropy up at those 2 values from this right here. So this is oxygen. Yeah, oxygen. So we need to use the oxygen table. And so I said the table A8. And here we are. A8. There's water. This is A8. Here's oxygen. Diatomic oxygen, right? So we have 300. And here is our value that we want. And then we also have 1500. And here is the value that we want. No, sorry, wrong. I was looking at the wrong one. So right here, sorry about that. There you go. It's easy to make mistakes like that. See, we want the oxygen one right there, boom. And 1500, here you go. Is that what I had before? Yes, okay, great. So 6.4168 and 8.0649. So 6.4168. And I guess I'll go ahead and put the units, although it slows me down. It didn't slow me that far down. And this is the 8.0649. And these values are used in this S2 minus S1 is going to end up equaling ST2 minus ST1 minus R natural log of P2 over P1. Notably, they gave that to us, right? So let's see. And I think there was something I wanted to show in that table. So let me take a peek back at it here in a second. 6.4168. And then we're going to go minus, and then we need R, by the way. We need R. So I think that's table A.5, I think, for oxygen. So while we're back here, it might tell us somewhere here, reference. So you go, reference pressure only relevant for entropy as entropy as a function of temperature and pressure, with that right there. See, there you go. That's what the little asterisk I wanted to say, and a mass basis right there. So just even tells you there at the bottom. And we gotta get. Oh, I'm gonna go up here. Gas constants. And for oxygen, where we go? Oxygen, we have these. Boom. I'll highlight them. So R is 0.2598. And those are also, what are they doing? Get down. kilojoules per kilogram degree Kelvin. So we'll put this in here, see if we can squeeze in 0.2598. Natural log P2 is 150. You notice it went down over 200. Right? So anytime you have this ratio and take a natural log, and you try this yourself, you'll note that having a number that's going to be less than 1 is going to make this a negative result. So we have a negative and negative. So that's good news that they will just end up being added to the thing. So I'm going to put a little thought bubble around here because it was a little departure. So your S2 minus S1, or I should just set delta S, whatever, is going to end up being 1.723 kilojoule per kilogram degree Kelvin. So even though there is the ideal gas assumption taking place right here, and that by that alone means that this is an approximation of sorts, we're going to say that this is the one we're going to compare the other two methods to. All right. So this is the method, we could call this, we're saying that we're going to use, this is the standard entropy. This next method, we'll use the easiest one with constant specific heat. And we were just looking at this, so we could have written it down. But that's going to be used in the equation that's S2 minus S1, which I could have just written in. And it's going to be C, I'm trying to see which one I use right here. Yeah, CP ln of T2 over T1 minus R ln of P2 minus P1. And noticeably, I could probably have just calculated what that value is because it's going to be the same value here. Here's really the thing that we're changing. Instead of using this from this table, not this table, but this other table, this table up here, we're going to go ahead and use this from this table. So we have a CP that we could have just written down a second ago. And that's going to be for oxygen, CP is going to be 0.922. 0.922. Go back up. There you go. And these units are kilojoules per kilogram degree Kelvin as well. All right, so plug those in. I'm tired of writing these down. Ooh, my pencil's like slow. Slow motion. Okay. 0.922 natural log. Remember, these have to be in Kelvin, but they already were. 1500 over 300. And then minus the 0.2598 natural log of 150 over 200. And we get 1.5586 kilojoules per kilogram. It's a kilojoule per Kelvin. Right? So that's not a great approximation right here. It's a pretty wide range of temperatures and a fairly high temperature. So that can, you know, some of those can factor into having a variation of CP. Notably that this is 9.54% less than the previous method. And let's go for the other one to do. Now this is the most annoying one, but we will just go ahead and plow ahead. Table A6, I think that's the one right there. Now we will see for, so this is A here. So we have for oxygen, these values right there that fit into this equation right there, right? So I'm going to write these down as I'm mentioning them. We have CO 0.88. We have C1 negative 0.0001. C2 0.54. C3 negative 0.56. F23. All right, and we have to write out the equation. Sure, might as well. I'll write it down here. Just because you can't see me, I'll do it. Right. Oh, come on back. Come on back, screen. So remember that's CO plus C1 theta plus C2 theta squared plus C3 theta cubed. And let's say that theta 1 is going to be 300 divided by 1,000. It's 0.3. Theta 2 is going to be 1,500 divided by 1,000, which is 1.5. And we're going to plug that into the main equation. Okay, and say that our delta S is going to be equal to the integral of Cp dt over t minus r ln p2 over p1. And notably that this can also be written as Cp d theta over theta, right? So there's nothing stopping us from doing that, right? So there's the incremental temperature. So we just divided both of these by 1,000, so it doesn't really matter. Rn ln p2 minus p1, but it helps conceptually to maybe just to write it down to remember what we're doing. So delta S is now going to be equal to this big ugly thing. We're going to integrate from theta 1 to theta 2. And I'm going to divide, and I guess, did I say this already? Yeah, okay. So I'm going to divide through by theta first. So we will, instead of integrating first, we'll just go here and note that we're going to go CO divided by theta, right? Because we're dividing all the way through by theta. And then the next one, we're just going to have C1 because we divided by theta right there. And then the next one, we're going to have C2 times theta. And then the next one, we're going to have C3 theta squared. And let's see, do I have anything else I need? And that's going to be d theta. So d theta can be distributed across all of those things. And then, of course, we'll just have this guy hanging out here going, why are you guys going through that problem? We just take a simple, I don't know. So anyway, we do the integration here, and I guess I tried to do it in one step. Was that smart? Probably not, but I'm going to go ahead and do it anyway. So we know that this is going to be 0.3. We know it's going to be 1.5, so we're going to put this one at 1.5 and minus 0.3 for all the ones that we do right here. And I guess I just got lazy, but that's okay. So we have this coefficient, 0.88, times the natural log, because we're doing d theta over theta, and here's the constant right there. And so we're going to have, in terms of the values we put in, that's going to be 1.5 divided by 0.3. All right, so we skipped a integration thing. And then this next, we're going to put in this guy. So he's a negative 0.1231. And we're just going to go ahead and put in this one minus this one, because this would just integrate into just theta right there, right? So I just wrote it wrong, 1.5 minus 0.3. Okay, so we took care of that. So this one's going to be this squared, and then we're going to have 1/2 this times there. So we're going to go plus 1/2 C2 0.54, and it's going to be each of these squared, right? So we're going to have 1.5 squared minus 0.3 squared. All right, so we took care of that one. And this last one is going to be cubed. We're going to have 1/3 in front of here, and then this thing's going to be cubed. But this one's negative right here, so we'll go put the negative right in there. I'll put the 1/3 here, put the 0.33 there, and then similar to this, 1.5 cubed minus 0.3 cubed, boom. And don't forget to put him back into here too, but I ran out of room, so I'm going to stick him over this way. And 0.2598 natural log of 150 over 200. Now there's a lot of opportunities to make a math error all the way through there, but I can confirm, because I made them like 4 or 5 times, and I don't know if it's 5 times, maybe it's like 3 or 4 times. 1.7059, and these are kilojoules per kilogram degree Kelvin. And so now we can compare this one. Don't need to compare it to this one because we know that's a pretty much an approximation. But we can compare it to this guy right here. So that's 1.723 compared to 1.7059, and this is about 0.996% less than the first method. I don't know another way to write it. The first method. So there's a comparison of treatments to get to handle that specific heat, right? Whether to make it constant, which is definitely the easiest way, to use this thing that we call the standard entropy method, or we can go ahead and integrate this one. We don't want to do that one. That was boring and yucky. We don't like it. So we'll do another example in the next video.